The code for the Lancer is not that complex. However, there are a few gotchas when working with the ATtiny85. So let's take a look at what we have in here so far. First, we actually have a few defines. In this case, we are setting a maximum PWM value for the LED driver. In other words, what is the overall brightness? The maximum brightness is actually 65,535 due to it being a 16-bit value. However, notice that I'm driving it at 40,000. And typically, when you're driving LEDs, you want to do something called underdriving the LEDs to kind of preserve the life of the LEDs. The next thing is I'll have a couple defines, arc select output and arc select input. These are the pins on board the ATtiny85 that are going to emit the current that is going to be detected by the button that changes the arcs. Here, we are initializing our TLC 59711 object from the library, which I modified earlier to not use the standard Arduino SPI. And then I have a few variables. This array actually contains a list of every single channel on board the LED driver that I'm using to drive one of the engines. And then this list contains, this array contains a list of every single LED channel that I'm using to drive any of the firing arcs. And then finally, the white LEDs that are going to be part of the headlights are going to be set to channel 2. So those are kind of like the basic things, and the basic operation is this. I have an index that says which arc is currently lit up, and inside of the loop, the first loop here inside of the main loop for the Arduino sets each of the engine channels to the maximum PWM value, and then I subtract a random value between 0 and 10,000, and this is going to provide a little bit of random flicker to each of those LED channels. Next, I'm doing this, I'm taking every single firing arc and then setting it to 0, and then for the arc that is currently selected, I am setting it to the maximum PWM value. Finally, I am going to set the LED channel that is the headlights to the maximum PWM value. And then the important line of code here that says tlc.write is where it takes every single one of these channel settings and actually writes it to the LED controller to light it up. And then I have a short delay of 200 milliseconds. To get the button to operate, I have to, first of all, take the output pin where I've connected one end of the button and take it and turn it into what's called the output pin mode. In other words, I'm going to be able to write voltage out. And then I'm going to set that voltage level to be high. In other words, it's going to put out 3.3 volts. And then for the arc select, I'm going to take that particular pin where I'm reading the voltage across the button, and I'm going to select that, set that to input. Now, if you're new to Arduino programming and you've never used an interrupt, a lot of people basically say, well, why don't I just read the state of the pin inside of the loop? In other words, just continuously read the state of the pin. And the reason why is because of this delay that says 200. Basically, if you put a delay inside of the loop and then at the beginning of the loop try to read the state of the pin with a digital read command, then that read is only going to happen once every 200 milliseconds. And it can be worse if the delay is longer. So it's not particularly responsive. So instead, in electronics programming, we use an interrupt, which is basically a way of saying that when an event happens on one of the pins, we're going to run some code asynchronously from the rest of the code. In other words, it's going to preempt the normal loop, basically just kind of put it on pause, if you will, sidestep, and then run code. So the way interrupts work is that we have to attach a function called an interrupt handler to one of the pins and have an event that it's tied to. In this case, I'm using this function that says attach PCInt, and I'm saying which pin to attach the interrupt to. And then the function that I'm going to run is this one called interrupt handler, which is defined up here. And then the event is that when the current is rising, in other words, when the signal goes from 0 up to 3.3 volts, rather than if it's pressed down, then it's going to actually trigger the code inside of the interrupt handler. So let's take a look at the interrupt handler code. Here I have a variable called volatile int clicks equals 0, and this is a normal integer that keeps track of the number of times that the interrupt has happened, but you'll notice that I've marked it as volatile. So volatile basically means that this particular variable can change due to code being run inside of an interrupt, and that normal code that's running inside of the loop should expect it to change at some point. All that's happening inside of the interrupt is that it's increasing the number of clicks detected by 1. So that basically means that if the code is running, it could be in the middle of the delay, it could be in the middle of writing a channel. As soon as I hit the button, basically it'll increase the number of clicks detected by 1. Now that means that inside of my loop, notice that I don't do any work. I don't actually change the arcs or anything inside of here, although it's certainly possible that I could change the arc index. I'm checking to see if any clicks were registered, reset the click count, and then I'm taking the arc index, which has to be between 0 and 3, because that's the number of arc channels, and I'm increasing it by 1, and then taking the remainder of it divided by 4. So that basically means that if it goes up to 4, it'll drop back down. So that is how I do the arc change. So about interrupts. Typically on an Arduino, you're going to have certain pins that are available for interrupts. And on the AT-Tiny85, it turns out that only 2 is set for what's called the normal hardware interrupt. That basically means I had to download an extra library for something called a pin change interrupt feature. The AT-Tiny85 actually has pin change interrupts available on every single one of its pins, but to access them I had to download this particular library by this guy named Nico Hood, which allows you to access the pin change interrupts. It has quite a bit of low-level C code, and this one does happen to handle pin change interrupts for a variety of different boards, including the AT-Tiny85. So this is not part of the standard Arduino interrupt library, which is actually quite a bit simpler to use. If this is intimidating to you, don't worry, I'm going to post all of this code on GitHub. We're going to need to make one more hardware modification to get this code to work reliably, and that's to add what's called a pull-down resistor. We're adding a 47 kilo ohm resistor between pin number 4 and the ground. Without this pull-down resistor, the level of voltage being read by pin number 4 would float between 0 and 3, causing some phantom turret arc changes that we don't want. Other microcontrollers have an internal pull-down resistor that can be set through code. However, in this case the AT-Tiny85 does not, and we're going to need that pull-down resistor to get our arc changes to function reliably. Finally, we need a way of pinning the model's turret onto the push button switch. I'm using the tiny drill bit by hand to drill all the way through the plastic of the turret, but only into the plastic portion of the push button switch to make sure that I don't damage the electronics or interfere with its operation. Later, during final assembly, I'll glue the turret and the button together using a little piece of the drill bit to hold them together.